Welcome everyone. My name is Eugenio Pescimoro and I'm a PhD student at the Faculty of Applied Mathematics at the University of Nottingham. And today I'm going to talk about the emergence of non-Fickian transport in truncated pluri-Gaussian permeability fields. Okay, so let's try to understand where does the problem in the research question come from. For a certain number of activities, such as oil recoveries and gas extraction, or carbon capture and storage, or again some groundwater remediation strategies, there is a need of reliable numerical simulation, which requires some good mathematical models. And these models, at least at the microscale, were tested and accepted, and these are the well-known Navier-Stokes equation, while at the Darcy scale or the heterogeneity scale, we use the Darcy law for simulating the flow and the advection diffusion equation for simulating the transport. But what do we use at the field scale if we want to simulate the flow and transport through porous media? Our research question then is, how can solute transport be modeled in highly heterogeneous porous media at the macro scale? On the left side of the slide, you see this portion of an aquifer where the different colors indicates different types of sediment or phases with different geological properties. And on the central panel, you can see a simulation of flow and transport in the same portion of the aquifer, while on the right side of the panel there is the so-called breakthrough curves, so the recording in time of the average concentration on the outlet boundary. As we will see later, this breakthrough curve is central and fundamental in the study of the late and early arrival times of the solute, which are usually the most difficult part of transport to be modeled. Our main tool to investigate flow and transport in porous media are numerical simulation performed in OpenFOAM, for which we have developed some geostatistical utility to reproduce the geological pattern, and we have adapted some solver, numerical solver for flow and transport, and these can be found at the link in the slide. In this process of simulating flow and transport, the very first step is to be able to reproduce the heterogeneity of the subsoil. So how do we go from the image on top to the one at the bottom? We go from the reality, as you see in step 1, to its geological and numerical representation in step 5. We adopted a method called pluri-Gaussian simulation, and it can be divided into 5 steps. So after observing the reality, the geologists provide a conceptual model of it, as you can see in step 2, and let's see what happened from step 3 to step 5. The chart which was shown in step 3 is the so-called lithotype or truncation rule that is now here at the center of the slide, and this chart is particularly relevant since it allows to summarize all the main aspects of the geological conceptual model of step 2, such as the contact between the sediments and their volumetric fractions. So once we have the Gaussian random fields, which are continuous and they can have different correlation functions. We enter at each location of this field Z1 and Z2 on the left, and with the values that we found at each location, we can assign a unique value given by the chart, and the resulting field is no longer continuous, while it's characterized by by this discontinuity that you can observe on the field on the right side. And in our for our experiment, we used the exponential correlation function. Coming at our numerical experiment, we wanted to test the influence of the permeability contrast and the correlation length and the Peclet number on the transport. So in order to do that, we generated a very simple geometry, as you can see on the low left corner, and using the equation at the mesoscale that are the Darcy law for flow and the advection dispersion for transport, we simulated the transport of a solute in this cubic domain with three different sets of parameters. So in the low permeability contrast case, the permeability difference between one sediment and another is 1 order of magnitude, while in the high permeability contrast case, there are 2 orders of magnitude difference between the permeability values. For each of these 2 permeability contrast cases, we had we were changing the longitudinal correlation length of the phases and the molecular diffusion coefficient. Let's see how accurately the macrodispersion model compares with the numerical experiment, the results from the numerical experiment. So as you can see on the left, the continuous line, which is the result of the numerical experiment, is interpolated quite accurately by different with using different interpolation techniques that go from the moment method to different type of least square, while on the right side panel the breakthrough curves that is in the continuous line in gray can be interpolated by any interpolation method, and the influence of the correlation length is slightly evident in the low contrast case. As you see on the left side panel, the breakthrough curves are shifting towards earlier arrival, and the peak is increasing, but in quite gradually. While in case of a combination between the high permeability contrast and an increasing of correlation length, these breakthrough curves become much more irregular and tend to reproduce the curve that we saw in the previous slide, which were not that was not possible to interpolate using different methods. Eventually, we wanted to investigate the influence of Peclet number on the solute transport in porous medium, and we did so by changing the molecular diffusion coefficient. And as you can observe in the low permeability contrast case on the left, the breakthrough curves are still quite smooth and regular, while on the right side of the panel, where the sediment have two orders of contrast between the permeability values, the curves exhibit quite an irregular behavior, which is hard to be interpolated by a macrodispersion model. And the reason is the importance of the advection, which prevail on diffusion, and creates some preferential flow path that anticipate the solid arrival. The take-home message of this presentation is that the permeability contrast plays a primary role when it comes to the fate of the solid, because the Peclet number and the correlation length, they do have an impact on transport, but it's not as important as the permeability contrast of the sediment. And our future works are to observe the transport in more realistic injection scenarios, but also to try to perform some numerical simulation using variable density and different hydrodynamic dispersion models, and also see what the impact of different lithotypes rule could be on the transport, and eventually try to calibrate and fit more sophisticated macro transport models. Thank you for the attention.